So if we take a look at the most common elements that we find in the human body, you can see that carbon, hydrogen, oxygen, and nitrogen, I like to remember it as CHON, are the major ones. 96.1% of the human body is made up of these elements. Now, there are some lesser elements like calcium, phosphorus, potassium, sulfur, etc. And you can see these make up a smaller amount of the body. So our next objective is to define molecule and distinguish between a compound and a mixture, and talk about solutions, colloids, and suspensions. So when we combine atoms together chemically, if it's just two or more atoms bonded together, we call that a molecule. If it's two or more different elements bonded together, usually in some kind of ratio, we call that a compound. So a compound is always a molecule, but a molecule is not always a compound because, for example, you can have N2 and H2. Those are two molecules of hydrogen with H2, and N2 is two molecules of nitrogen bound together. Those are molecules, but they're not compounds because they're not different elements bonded together. Okay, so what about mixtures? So in this picture, we have some different kinds of mixtures, but how do we define a mixture? In a mixture, as opposed to a compound, there's no chemical bonding. So things can be separated physically. So a salad is a mixture. So things can be separated by straining, filtering, maybe evaporating off one of the solutions, or the solutes, I should say. And these mixtures can be heterogeneous. They can be, so heterogeneous means unevenly mixed, so clumpy, kind of like a salad if you haven't mixed it well, or homogeneous, evenly mixed. So the components of the mixture are evenly distributed. So this is as opposed to compounds that we talked about before. Compounds are chemically bonded. You can't separate them unless you're breaking chemical bonds, and they're all considered homogeneous. So we can see here we have three different kinds of mixtures. And so we have solutions, colloids, and suspensions. So solutions are what you get if you take table salt and you dissolve it in water. The table salt would be called the solute, and the water would be called, what you're dissolving it in would be called the solvent. So the particles, these molecules are tiny, and they become evenly distributed in the water. And so they don't settle out, they remain in suspension, and they don't scatter light. So anytime you have water with dissolved solutes like glucose or table sugar, sucrose, salts, those are all solutions. A colloid is more like a gel. So the solute particles are bigger and they scatter light. So if you shine a light through the solution, it would just pass right through. If you shine a light through the jello, it may scatter that light some more because the solute particles are larger and less evenly distributed. And so in the colloid, these solutes also don't settle out. So if you just left this jello here, the components that are in this jello don't settle to the bottom. So some examples of a colloid are the jello shown in this picture, but also the cytosol, the portion of your cell where we find a lot of the organelles suspended in. And then a suspension is our third type of mixture. I like to think of this as maybe the mixtures you went out as a kid and made in a pot, like the mud soups that you made, where you just took water and leaves and rocks and a bunch of other stuff and mixed it all up. And if you didn't keep mixing it, it would settle to the bottom. So in a suspension, you've got large components, they can settle out, and it's hard to shine a light through a lot of suspensions because they scatter light. An example of a suspension in our body is blood. So cells, like red blood cells and white blood cells, they will settle to the bottom if left without mixing. All right, so our next objective is chemical bonds. So I want to take a look at chemical bonds and the octet rule. So let's take a quick look at our periodic table again. Okay, so here's our periodic table of the elements. And this periodic table is quite nice because it gives us some information on the electrons, where we can find electrons. So in terms of chemical bonds, the only electrons that interact in chemical bonds are the ones in the outer shells, which are also called the valence shells. And so in this particular periodic table, it shows us that what are the number of electrons in the outermost shell. And so we can see with hydrogen it's 1, with helium it's 2. So I'm looking at this little number right up here in the corner. These different levels represent, so 1, 2, 3, 4, 5, 6, 7, represent different levels of electron shells. And so we can see in lithium, this first electron shell is filled with 2 electrons, and then we've got 1 electron in this outer shell. And then beryllium has 2 electrons in that full inner shell and 2 electrons in the outer shell. In the first electron shell, you can only have 2 electrons. In all other electron shells, you can have a maximum of 8 electrons in that outer shell. So 8 is the magic number here. If you have an atom that has 8 electrons in its outermost shell, it tends to not want to react with any other element. So these noble gases over here, these are not very reactive elements. Whereas things that have, like sodium, that have 1 electron in their outermost shell, and chlorine that needs 1 electron, so it's got 7 in its outermost shell, that needs 1 electron in its outermost shell, they tend to be much more reactive and form molecules and compounds. So you can see some of these transitional metals in between have what we call different orbitals, but you can see they still never get more than 8 electrons in their outer shell. So for most of these levels of the periodic table, you can kind of skip over the transition elements. and you can just count across and know how many electrons are in the outer shell. For example, sodium will have 1, magnesium will have 2, aluminum will have 3, 4, 5, 6, 7, 8. Okay, so what are our major types of chemical bonds? We have ionic bonds, covalent bonds, and hydrogen bonds. In an ionic bond, what happens is we end up transferring a valence shell or outer shell electron between these atoms. And so one electron is actually moved from one atom to the other. And so the example in your book, sodium and chlorine, sodium has 1 electron in its outer shell. Chlorine has 7 electrons in its outer shell. And often they say chlorine steals that electron and completes its outer shell. That electron is gone. That 1 electron is gone from the sodium outer shell. And so the next shell down is completely filled. And since sodium has a lost an electron, that's losing a negative charge, it becomes positively charged. Chlorine has gained an electron, and so electrons are negatively charged, so it's got a negative charge. And basically what holds these bonds together are opposites attract, so electrostatic forces, attraction of opposite charges. And so this forms a new molecule. And in this molecule, we have a positively charged cation and a negatively charged anion, the sodium ion and the chloride ion, to form sodium chloride. Now, another major type chemical bond is the covalent bond. And this is when atoms share 2 or more valence electrons, and that forms a new molecule or compound. Most of our molecules and compounds in our bodies are going to be covalent bonds. So things like glucose, proteins, lipids, they're all covalent bonds. So in this case, we've got hydrogen, which has 1 atom in its outer shell, carbon, which has 4 electrons in its outer shell, and carbon is going to share one of its outer shell electrons with hydrogen, and hydrogen is going to share one of its outer shell electrons with carbon. Now, in order to fill the outer shell of carbon, carbon has 4 electrons in its outer shell. It's going to need to share with 4 hydrogen atoms. And so each of these molecules gets to share 1 electron with each other, completing the outer shells of both of these different atoms. Covalent bonds are quite strong. Okay, so here's another example of a covalent bond. So we've got 1, 2, 3, 4, 5. And so it needs 3 more electrons in its outer shell to be less reactive, to be stable. And so it can share 3 electrons with another nitrogen molecule and form a covalent bond. And so each of these nitrogen molecules is then going to have 1, 2, 3, 4, 5, 6, 7, 8 electrons in the outer shell. Some molecules are considered polar, and some molecules are considered nonpolar. So a nonpolar molecule tend to be linear, they tend to be symmetrical, they tend to have similar charges all the way across the molecule. So there's not one end of the molecule that's more positively charged or negatively charged. Polar molecules tend to be bent in shape, and they tend to have an unequal distribution of charges. So for example, water has a negative charge on the oxygen end of things and a positive charge on the hydrogen end of things. This is because some atoms, like oxygen, are more electronegative. They don't share equally, and so they pull the electrons from the hydrogen atoms closer to their nucleus, and so that pulls those negative charges closer to this oxygen side of things and away from the hydrogen side of things, making these ends of the molecule more positive. And so what ends up happening is polar molecules and nonpolar molecules have different properties, and water in particular can form what are called hydrogen bonds. So hydrogen bonds are weak interactions between positively charged and negatively charged sides of these molecules. And these are weak bonds. That's why they're drawn as dotted line or a dashed line quite often. And they're constantly breaking and reforming. If you're looking at a glass of water, they are breaking and reforming, but they are responsible for some of the properties of water, like surface tension, and the fact that it is hard. It takes a lot of energy to boil water, to turn water into steam, because they've got all these hydrogen bonds holding the molecules